Hi everyone, welcome to another lecture of control systems. In today's class, we're going to see what is a time response analysis. Right. So this unit is dedicated to studying the time response for various inputs and various orders of the system. And to define what is your time response is nothing but a behavior of a system over a time period or a duration. So the behavior of the systems can be categorized into two. It can be either a steady state behavior, where your output is constant over an interval of time, or it can have a dynamic or a transient behavior. So we're going to see time response for both the steady state as well as your transient systems in this unit. So now, what I can talk about in terms of just the introduction of your time response analysis is your time response analysis allows us to study the system irrespective of the input and the output. So as you will be seeing, time response analysis mostly work with Laplace transform or S domain. So the S plane, and you have poles and zeros. So we'll be seeing in depth on these poles and zeros in the coming classes. But what I can tell you is the system is dependent on the poles, and the characteristic of the system is not affected by the input. So by doing this time response analysis or by doing this S-plane level modeling of your system, I am making sure that my system's characteristic is what I want to be, or it is not controlled by the input. My system behaves the way that I intended to behave, because I am the designer of that system and I have designed that system for a particular purpose. Because there is no way to know what your input is going to be, because once the system is put into actual use, once the system is out there in the real world, in a real system, let's say in an aircraft, in a defense system, in a radar, or in a satellite. So you don't have, there's no way you can know what your input signal is going to come. Your input can be anything, or it can be what you predicted it to be, or it can be something totally different. So your system characteristics will decide how. So your character of the system is going to define how it handles those inputs. All right. So this time response analysis goes a long way to help us in studying the characteristics of the system and designing and modeling your control system. Good. So let's get started with that intro for time response analysis. We will see today in detail of these time systems. So let's get started with our closed loop transfer function. And this is very important for my time response analysis, because my closed loop transfer function is what gives my time response. So you'll be seeing it how. So any transfer function is defined as the gain, and it is an output response divided by the input response. And when I say transfer function, it can be in S-plane, right? So let me take a closed loop transfer function. So when I say it is a closed loop transfer function, I'm talking about a system G of S, then I'm talking about a feedback control H of S, and then your output response is C of S, and your input response is R of S. So now what is our closed loop transfer function for this? So this is the control system. So this is your system. I'm talking about transients. I'm talking about steady state, dynamic, transient responses. So you want a steady state system, you design a system like this. You want a transient system, the same system can be made to be a transient system. So just, as a simple example would be to change from negative feedback to positive feedback. So that would take your system from steady state. For a negative feedback, you normally get a steady state system, and for positive feedback, you get a dynamic or a transient system. Good. So now I'm deriving the transfer function on the right hand side here. So my C of S by R of S, we know from our negative feedback formula, it is given by G of S divided by 1 plus G of S into H of S. That is the system divided by 1 plus system into feedback. And now, what is the time response? So how our time response that we are seeing in this unit is related to our closed loop transfer function. So the time response L inverse of C of S is equal to C of T. And now your C of T is your time response. Got it. So what I've done is in my transfer function, and that is my output response is my C of S, and then I have to take the inverse Laplace transform, that is my L inverse, that is my inverse Laplace transform of C of S. That is going to give me my time response. And how do I get that inverse of C of S? By taking the system level function. System level function is your transfer function, right? A transfer function which contains my system blocks G of S and also the feedback control H of S, and that is the equation I will be using to compute my time response C of T. Now, before we get into the time response modeling of your systems, we need to understand a few things, few basic things. Laplace transform of a standard test signals. Some of you might already know this, but for those who are new to this, I'll introduce to you. So the two important signals that we have in this system modeling or in this time response analysis are your impulse and your step signal. So like always, a system, a response at the time response to an impulse signal is very famously known as the impulse response of your system. So you must have heard of this word impulse response in many places. Then for a step signal, your response is step response. So the impulse response and step response are the most basic tests that we use on any system to decide on certain properties and to study the stability, causality, or just to understand how the system is working, what is the time response or the behavior of your system. So the Laplace transform of my impulse signal is just unity or 1, and for my and its response is known as my impulse response. Then for my step signal, the response is step response, and the Laplace transform of a step signal is 1 by S. So where do these inputs, where do these standard test signals come in my time response? Right, if I go back to my closed loop transfer function, if I look at that equation, I have my C of S by or R of S, and that R of S is nothing but my input, right? That is the Laplace transform of my input, and my input, if I am using an impulse signal, then my response is impulse response, and R of S is equal to 1, and if I am using a step signal, my R of S is equal to 1 by S. Next, for signal O3, I have my ramp signal, which is the Laplace transform of a ramp, or a slope signal. You know this, what is a ramp signal? It is just a slope signal, and the Laplace transform is 1 by S square, a less significant signal for control systems, and a parabolic signal, it is 1 by S cube. So we are not really bothering about these two signals because we are more interested in the step response and the impulse response. So we'll be seeing a lot more of step and impulse in the coming classes. Next is the order of a control system. So here this order, the order that we are talking about here is about your control system, and it is not the same as a mathematical order or the order in your mathematical linear systems you have seen till now. So what is the order of a control system? So in control system, we are telling, we will just decide on the order of the system by Q of S by P of S. Right, so what do I do is I'm writing what is the differential form, or what I can do is I can make a control system design in this manner. It is of order, not order, I'll just say power, s to the power of n and s to the power of m. So the differential mapping is s to the power of n is differential of n, right? D to the power of n by d2 to the power of n, and s to the power of m is d to the power of m by dt to the power of m. So now let us assume one of this, it can be any, it can be either P or Q. Let's assume one of this is our input and one of this is the output, and the transfer function is given by the output by input. Now the order of your control system for such a system or for such a design is going to be the maximum power of the denominator. The maximum power of S in your denominator is the order of the system. So in this case, if I am taking Q of S, which is in the denominator, the maximum power of Q of S is going to be what? N, right? So the maximum power of system is not M. I think it is N. So we got it wrong there. So it is N. Okay. So let's do these examples that should clear the ideas for you. Let us take an example here. Yeah, there I got it wrong. S plus 1 by S square plus 2. So what is the order of this is 2. The order is 1. Then S plus 4 divided by 2, the order is 0. Okay, good. Denominator always. Now, why this order? Where do you get this order from? So we have not yet started on the zero pole analysis, which is very important, very crucial for your control system behavior or time response. So I'll just tell briefly that if you have a pole zero form for your control system, your zeros are coming in the numerator and the poles are placed in the denominator. So the order of the control system in Laplace domain are only dependent on the system poles. So that is a very important thing to know, and that is why your order is given by the highest power in your denominator. Excellent. Good. So now we will go to studying some of the systems based on the order. So we have seen your first order system, which is given by k divided by st plus 1. So this is your first order system. K can be just a constant gain. We can assume k to be 1, and t is your time constant. So we'll be seeing what a time constant is. So for your second order system, it is going to be just k into st plus 1. So this k and t are chosen mainly because we are attaching a steady state gain, because the gain is controlled with k, and then the t is the time constant. So the time constant tells you how fast your system is. So it is for the speed of your system. So let us say I am having a motor, I am running the motor, and the motor has to go from 0 to 100 RPM in like 5 seconds. So that 5 second is decided by this time constant. So if I want to make the system faster, I want to go from 0 to 100 RPMs in just 1 second. What do I need to know? What do I need to do in my system is to modify this time constant, to change the time constant that will make my system faster or slower. Good. So that is the significance of your time constant. Now let us, what we are going to see here is we are going to see first order system and second order system in this unit, because that is the mostly used control systems designs. So we will be seeing these two. So a first order system can be represented in a feedback control form in this manner. So you have always your input to be R of S and your output to be C of S, and now your system is 1 by Ts. So this is your first order system because the power of S in the denominator is 1, and then you have a unity feedback. So your feedback is now unity, or your feedback is 1. So that is what it means. Now what is our closed loop transfer function? So what is the transfer function C of S by R of S? And that is given by 1 by Ts divided by 1 plus 1 by Ts into 1. Good. So now this is what we have as your closed loop transfer function, and that simplifies to 1 upon Ts plus 1. So that is your first order transfer function. So the k, the gain, I'm keeping it as unity. We will come to that later. But now what the time constant? T is your time constant, and then the other thing, S is your Laplace S plane. So into K, I'm writing it as a steady state K. Good. Now, the first order system's properties. The first order transfer function is given by this, right? 1 by ts plus 1 plus 1, where your K can be unity or non-unity. So now what we have to do is we are going to find your impulse response and the step response to a first order system. Okay, so the assumption of unity gain is what makes that K equal to 1. So done. So this is the block diagram of your first order system. And now for this given first order system, or the first denoted first order system, we want to find what is the impulse response. So the impulse response of your first order system is given as what? So the impulse response, in order to find the impulse response, we need to find the input R of S to be an impulse signal, right? We have to keep our input R of S to be an input signal. That means our R of S for an impulse signal is what? Is equal to 1. Yes, right. So that is the substitution I'll be doing into my first order system, which will then give me an expression for C of S, right? Because R of S is something already we know, and we are substituting it. So now what is the response to that input? That is your C of S. And then what do we need to do? We need to take the inverse Laplace transform. So when I do the inverse Laplace transform for my C of S, I get my C of t, which is your impulse response, or which is your time response for the input signal, which is impulse. For the input signal to be an impulse, your response is given as C of t. So how do I find the inverse Laplace transform? So the inverse Laplace transform in this case is pretty straightforward. I am having certain formulas which come from the mathematical domain of Laplace transform. So I am not going to derive those for control systems. It's not needed, but we need to know these formulas. So I'll be writing these formulas in these boxes you see here. And as we go along, I'll be whatever formula that we are borrowing from Laplace transform will be written here, and that should be enough for you to solve any questions on these areas. So now applying the inverse Laplace formula, we get the impulse response. Next, we are looking into our step response. Step response of a first order system. So what is a step response? It is your time response when your input is unit step. So when your input is a step signal, what is the response? C of S, and that is what we are going to find here. And for my step signal, my response R of S is going to be 1 upon S, right? We have seen this in the Laplace transform of standard signals. Now I'm going to use that R of S is equal to 1 by S, and then I'm going to find my C of t. How do I do that? I take the inverse transform of C of S, right, with substitution of R of S is equal to 1 by S. So when I do that, I am getting my C of S to be equal to 1 by S into Ts plus 1. And now to simplify, so to get the step response, or to get the C of t, I need to apply my inverse Laplace formula. And I can tell this much, that my L inverse is not straightforward. So L inverse of C of S is my C of t, but I can tell you this much is, since I am having in the denominator, now my order is no longer my first order, right? So it is now a second order. The highest power is S square. So it is a second order system. And in order to solve the second order system, so we don't have a direct formula in inverse Laplace to solve the second order system. We have to separate this second order systems into two first order system. And how we separate a second order system into two first order system? Using partial fractions. Good. So what I am going to do here is I'm going to represent the RHS, or which is the second order system as the sum of two first order system, and this is your partial fraction separation, and it is applicable only to S because we are doing order splitting, right? We are reducing the order. We are taking a second order and splitting it into two first order, and so which means your order is applicable only to the S domain variable, and that is what we do here. Now, I'm pretty sure you have seen, many of you know what is partial fraction expansion and how to solve partial fraction in control systems, or in, you have seen this in plus two probably, but nevertheless, we will just see one or two examples on how to solve the partial fraction using this technique. I'm sure this is not the technique that you have used in your school days. This is a slightly different technique. The technique that I'll propose is in three steps. So the first step is to separate the S terms in the denominator to partial fraction sums. We have already done that. This is what it looks like. And now I'm going to do the step 2. So for my step 2, what I am going to do is I'm going to multiply my RHS, multiply the right hand side and the left hand side with the denominator of the left hand side. Alright, okay, good. So it's confusing, yeah, but when you see it, it makes sense. So what I'm doing is the denominator on the left hand side is S into S plus 1 by T. So I am multiplying it. So that is what I'm doing there. And I'm doing that on the both sides. So when I do it on the both sides, I'm going to get somewhat in this manner, right? So I'm going to get S into S plus 1 by T is plus 1 by T. And now let us see how this simplifies too. So I can see a lot of terms cancelling out, and then I can write the final equation as 1 by T is equal to AS into 1 plus T plus BS. Good. So this is the output or outcome of your step 2. So we are not done yet. So I've told you we have 3 steps. So the step 3 is where what I'm going to do is I'm going to equate the coefficients of starting from the highest power of S. So I'll just say I'm going to equate the coefficients starting from your highest power of S. So which means I'm going down till S to the power of 0. That is your constant. It becomes, right, when S to the power of 0, S vanishes. So you just have constant terms. So that is the idea of step 3. So we will apply step 3 to the equations that we have as an outcome of step 2, which is 1 by T is equal to A into S plus 1 by T plus BS. Now if I put the value of, take coefficients of S. So what I'm going to do is first start with highest S terms in my equation is S to the power of 1. So the coefficient of S I'm substituting is 0 equal to A plus B. Next, take the coefficient of constant or S to the power of 0, which is 1 by T is equal to A into 1 by T. So your A becomes equal to 1 and A plus B is equal to 0. Or your B is equal to minus 1. So now I get both my A and B from this coefficient substitution, which is your step 3. So after that, what we go back to our partial fraction splitting, right? So we go back to that term. So where I got this A by S plus B by S plus 1 by T. Now I know the value of A to be 1 and B to be minus 1. So I am just gonna use the first one and the last one. Because now if you see the order of the partial fraction expansion or partial fraction computed coefficients are just 1. So if I see simplification or substitution has brought down the order from 2 to 1, and that is having direct formulas. So we are having formulas for these direct, for these in inverse Laplace. So we will just apply those formulas and our thing. So now applying inverse to this, we will be getting as 1 minus e to the power of minus t by t, because those formulas are straightforward substitutions of my inverse Laplace formula. Good. So that is the idea. Now if you see, I am getting this 1 by s plus a is equal to e to the power of minus at. That is one formula I am using, and the Laplace inverse of 1 by s is equal to 1. So these are the formulas that we are borrowing from our inverse Laplace formulas. Done. So now that is your step response. It's a bit lengthy, but in your exams or in many questions they ask for both. They ask for the impulse response and the step response. Your control system paper without an impulse response and a step response, you will not be, you will not see a single semester paper. You will have at least one question from either step response or your impulse response. Now let us see how the graphs plot. So this was asked in one of the questions, is plot the graph for your step and impulse response. So they didn't ask you that derive this step and impulse response, but they were asking you to plot the graphs. And what what you have to do is you have to plot the graph. So the graph is going to look exponential because for your impulse response you had e to the power of minus t by t, and for step response you have 1 minus e to the power of minus t by t. So it's good to remember the impulse response terms and the step response term, because in the exam you don't have to recollect, you don't have to derive the whole thing to just draw the graph. So if the question is for drawing the graph, just draw the graph, and your graphs for this is going to look like an increasing exponential and a decreasing exponential. Just put some values of t and you can easily come up with this shape. So that is your first order response, right? The first order system response to your step and impulse. So here in this slide itself, I will do what I will do is I will plot the time constant also. The time constant is nothing, it is c of t versus t, and it just tells you the time taken by the system to reach the maximum output. So let us say you are, like I said, you are having a motor, the speed is maximum seat speed is 100 rpm. So what is the time the system takes to reach that speed? It could be 10 seconds, right? So that is controlled by, that can be controlled with the help of your time constant. So I can bring it down to 5. Yeah, when I do that, what is going to happen is the system is going to expecting more output in a short interval of time. It could damage your system, it could overheat your system, a lot of things. As the temperature goes up, the invertive feedback comes into play, and it will again reduce the system speed. So there are a lot of factors that need to be considered. So we just, plainly speaking, the time constant allows, it helps us to speed up or slow down the system. So that is your time constant t used in your first order system. So we don't use this time constant after the first order system. So the next topic will be second order system, and we are not going to see this time constant. So I thought I'll just show what a time constant is. Many questions in previous semesters they are asked so why you are using that t there, because we have seen using a t makes the system unstable. So that is why it is not called as a time variable, it is called as a time constant, right? So it means it is just as same as the constant, because anytime adding a constant or multiplying a constant is not going to affect the stability or the causality of the system. So the system is going to be stable as it is because it is a constant. So that is why we call it as a time constant. Now let's do a numerical which is a very typical numerical asked in your exam questions. We'll do that, and then we can that should be enough for today's class. So that covers your first. So today's class we will be seeing the whole of the first order system, and tomorrow the next lecture we'll go for the second order system. So the question is something like this: obtain the time response of a unity feedback system whose open loop transfer function is g of s is equal to 4 divided by s into s plus 5. So now there is what is here, they are telling it is a unity feedback system. So unity feedback system means your h of s is 1, and in the question they have given you g of s. So we have to find the transfer function, and the formula for transfer function is g of s divided by 1 plus g of s into 1. Alright, so now that substitution I am doing for g of s, is going to simplify this to 4 divided by s into s plus 5 plus 4. Good. Now again, okay, so what you have to find is, you have to find step response. See the last part of the question. Your input is a step signal. So when your input is a step signal, you have to find the step response. And how do you find the step response? Yes, you guessed it right. Put R of s is equal to 1 by s. So that is what I'm going to do here. I am going to put my R of s is equal to 1 by s, and then what else? And then let me see. So when I do that, I'm going to end up with a term. What is the order here? Oh, I'm having s cube. So when I simplify this for my step input, I'm getting s cube in the denominator, or I'm having a third order system, which means what? Your partial fraction expansion comes into play. So now I'm going to take this third order system and split it into 3 first order systems using partial fraction. So how do I write that? Okay, so before I do that, I can see I see that I have one more simplification here going on, which is my quadratic factorization. So this is also very elementary. All of you know this, but the class is meant for all the students. So even 1 or 2 students may not know this. But it's good. I just write it here. It is a sum product. So when I have a quadratic expression s square plus 5s plus 4, my 5 is the sum and 4 is the product. And then how do I factorize it? I look for factors which meet this criteria. They add up to 5 and they multiply up to 4. And that is the factors 4 and 1 I get. And now I am going to do the partial fraction. I'm going to take this third order and I'm going to convert it into 3 single orders. So this will become C of s is equal to 4 by s into s plus 1 into s plus 4. So this is equal to 4 by s into s plus 1 into s plus 4, and that is going to be converted into a by s plus b by s plus 1 plus c by s plus 4. I am going to do the same steps, the 3-step rules I have shown you for partial fraction expansion. So the partial fraction expansion at this steps, at the first order system, is conveniently done using only those 3 steps. But as we go higher up, so let us say take for a second order system, which we'll be seeing next, it gets little bit more complicated. So what I will do there is I may have, no, I'll introduce more rules. I'll introduce one more rule, to this 3-rule partial fraction simplification, and then I'll show you how to do it in that numerical or in that class. So for now, I'm just sticking to these 3 rules, and which means now after this, I'm going to multiply the right hand side and the left hand side with the denominator of my left hand side. So that is s into s plus 1 into s plus 4, s into s plus 1 into s plus 4. So I'm doing this, and then I'm eliminating common terms in the numerator and denominator throughout. And that means I get rid of these things. And then I'm writing the output of step 2. So that is going to be 4 is equal to a into s plus 1 into s plus 4 plus b into s plus 4 plus c into s plus 1. And now this will be, I'm going to multiply it, and then what I'll take this to step 3, where I'm going to start with the highest coefficient of s, equate it, and then go downwards till I reach s to the power 0 or constant terms. So I'm seeing I'll be having s square, that is the highest power, s to the power of 1, that is the second highest, and s to the power of 0 or my constant terms, that is the third power. So I square s to the power of 1, s to the power of 0. Doing that, I will get to the simplification. So s square terms will be written like this, C0, because I don't have any s square terms on my left hand side. So 0 is equal to a plus b plus c, and then moving on to s terms or s to the power of 1 terms. I don't have any on the left hand side, but on the right hand side I have 5a, 4b and c. And s to the power of 0 term, I just have my constant term. I have only 1 on the left hand side and the right hand side, and that gives me my a is equal to 1. So I have the other 2 equations now. Just using substitution and simultaneous equations, solving them as simultaneous equations, I get my b and c. So I should be getting my b to be minus 4 by right? So what will I get? I have to do the simultaneous substitution. So I think I'll get it as minus 4 by 3 and 1 by 3 by just looking at it. I'm telling. So let us see, let us simplify this. So I get 4b equal to minus 4 by 3, and yes, I get. So C, after that I get my C is to be what? 1 plus 4 by 3, that is going to be is 1 by 3. Good. So yes, so I have my A, B and C now, which converted my third order system into three first order systems, or sum of three first order systems. And then I can apply my inverse Laplace transform directly to these first order systems. They are straightforward formula substitution, and then I get my step response, that is C of t. So L inverse of C of S is applicable now, and that gives me my C of t, which is 1 minus 4 by 3 e to the power of minus 3 plus 1 by 3 e to the power of minus t. This is your step response. And you all know how I wrote this, because these are coming from my Laplace